Putting it together, the final trick. Theorem 11.1. Fermat's last theorem holds, that is, if a, b, c, and n are integers such as a to the n plus b to the n plus c to the n is equal to 0, and n is greater or equal to 3, then a, b, c is 0. More generally, the argument below establishes. Every semi-stable elliptic curve over Q is modular. Let E be the corresponding Frey elliptic curve. Consider its associated three-division representation rho bar from GQ to GL2 of F3. There are two possibilities. Either rho bar is irreducible or irreducible. Suppose first it is irreducible. Lemma 11.3. In this case, rho bar restricted to GQ of the square root of minus 3 is absolutely irreducible. Proof. Let H be the image of rho bar in PGL2 F3, which is isomorphic to S4. Suppose the lemma is false. Then H is not equal to S4, else P bar, rho bar, would be surjective by the exercise as follows. And then the image of GQ of the square root of minus 3 would be SL2 of F3, which is absolutely irreducible. We consider the subgroups of S4 in turn, first denoting that H is a subset of A4, which is isomorphic to PSL2 F3. It's impossible, since then the determinant of rho bar would be trivial. Additionally, H cannot be a subgroup of any S3, since then the image of rho bar in a Borel subgroup, and so rho bar is reducible, contradicting our hypothesis. This leaves only the possibilities that H is dihedral of order 8 or a subgroup of index 2 of this group. Since E is semi-stable at P not equal to 3, rho bar of IP has order 1 of 3. Since 3 does not divide the order of H, rho bar of IP has order 1. That is, rho bar can only be ramified at prime 3. Thus, the abelianization of H over H prime is the Galois group of an Albanian extension of Q of degree 4, ramified only at 3. By Kronecker-Weber, this has to be a subextension of some Q zeta 3 to the r, but this has a degree of a Q not divisible by 4, which completes the proof. The hypotheses of the general case are now satisfied, namely that we have a representation rho bar from GQ to GL2FL, where L is in fact 3, such that rho bar restricted to GK, where K is specifically chosen, is absolutely irreducible. And rho bar is semi-stable, which follows from the theory of Tate curves, and rho bar is modular, which follows from Langland's tunnel. Let sigma denote the set of primes that will divide ABC. Then P3 to the power infinity, which goes from GQ to GL2Z3, is a lift of a rho bar of type sigma. We showed in chapter 11 that R sigma to tau sigma is an isomorphism. This means that the universal map R sigma to Z3, producing P rho to the 3 infinity, actually factors through tau sigma. Hence, P3 to the power infinity is modular. That is, there exists a cuspidal eigenform f, such as TRP3 to the infinity of FRP equals APF for all but finitely many primes P. Next, consider Pn to the infinity from GQ to GL2Zn, where n is a Fermat exponent. Since TRPn to the infinity FRP equals TRP3 to the infinity FRP equals APF for all but finitely many primes P, it follows that Pn to the infinity is modular. Note Faulting's theorem is not needed for this result, and so Pn is modular too. We showed, however, that Pn is good at all primes not equal to 2, and semi-stable at 2, where n Pn is equals 2. By Ribet, Pn is then associated to be the cuspidal eigenform of level 2 and weight 2, and trivial Nebentypes, but there are none such. This contradiction concludes the proof, except for the matter of dealing with the possibility of rho bar being reducible. This possibility also troubled Wiles. Unable to handle it, He had the rest of his work typed up in the spring of 1993 with the amusing typo Fermats' lost theorem, when he spotted how an idea of Mazur would fix the problem. This called the 3-5 switch. If Wiles had not spotted this, then Elke's alternative approach of twisting curves would have finished off FLT. Theorem 11.4. Suppose rho 3 from GQ to GL2 F3 is reducible. Then rho 5 GQ to GL2 F5 is reducible. Proof. Suppose that both are reducible. Then EQ bar has a GQ stable subgroup of order 15. Under the 1-1 correspondence between Y0 and K and isomorphism classes of elliptic curves over a field K together with a subgroup of order n defined over K, this elliptic curve corresponds to a point Y015Q. Now, X015 has genus 1 and so is an elliptic curve. In fact, 15a in Krenemar's tables. Its rational points form a group of order 8. Of these 4 are cusps, so not in Y015Q, whereas the other 4 correspond to elliptic curves of conductive 50, which are therefore not semi-stable. QED. A similar calculation to the first lemma above shows that P5 restricted to GQ of the square root of 5 is absolutely irreducible. Rho 5 is also semi-stable since E is. The only thing missing is that we do not know that it is modular. Since GL2 F5 is non-solvable, the Langlands tunnel approach fails, and we need to take an alternative route. Theorem 11.5. Dubbed the 3-5 switch. There exists a semi-stable elliptic curve A over Q such that A5 is isomorphic to E5 as GQ modules and A3 is irreducible as a GQ module. Once this is proven, then, by the theorem proven so far, A is modular, so its rho 5 is modular, but this is the same rho 5 as for E, thus the missing piece is filled in. Proof. The idea is to consider the collection of all elliptic curve A such that A5 is isomorphic to E5 as GQ modules by an isomorphism pi. That makes the diagram of Wiles pairings commute. This diagram is described by A5 times A5, which maps to E5 times E5 by the map pi times pi. Both A5 times A5 and E5 times E5 map to mu5. Note that this is in 1-1 correspondence with a curve Y prime, which is a twist of Y5, so of genus 0. This allows us to use Hilbert's irreducibility theorem to complete the proof.